All right, hey, what's up, everyone? Unfortunately, I will be out of town this week. I will be escorting the soils judging team to Knoxville to compete in the regional soil judging contest. What I did is I posted calculation 2, and I just wanted to kind of go over some of that math with you because I'm not there in person. I do want to tell you that we will not have class on Monday or Wednesday, but I will be back Friday, and I would like to go over some of the information that's been kind of given through video. I'd like to do that in person because when you come back from fall break on that Wednesday, we're going to have exam 2. So I'd appreciate it if y'all showed up Friday so maybe we can get some clarification about those things that were missed while I was out with COVID. All right, so we're going to go over base saturation, relative neutralizing value, and fertilizer cost. So when we're talking about calculating our cation exchange capacity, the CEC, and our percent base saturation, all this really is just a little bit of math. And kind of the way that we go about doing that is we will sum the acids. So our acids being hydrogen and aluminum. So go ahead and sum all your hydrogens and your aluminums. $33 and $13 is $46. We do that all the way down. And we have calculated the amount of acid cations that we have in this soil. Next, we want to calculate the base cations, and the bases being everything but hydrogen and aluminum. And if you notice, this is part of the lyotropic series. So calcium, magnesium, potassium, ammonium, and sodium. So when we do the math across there and calculate that, we get, let's say we'll just work with Horizon 1. We have 110 centimoles of charge for our base cations. Combine those two together to form the CEC. This is the total cation exchange capacity of that soil. That is 156. Next, we're just going to take the percentage of that 156, the percentage of the total CEC that is comprised of bases only. So 110 divided by 156, and that is going to give us 70.51. All right. So next we're going to move into how we go about determining lime requirement. Like I'm going to go over this again a lot more in class, probably 2 Fridays from now when we make it back to into module 3. But anyhow, we have this liming requirement that is going to neutralize some of our acidity, and the way that we go about calculating how much lime we need, the soil test is going to give us a recommendation of pure 100% calcium carbonate. However, the co-op might not have exactly pure 100% calcium carbonate. Much like our fertilizers, there's less nutrient or calcium carbonate in those materials. The things we need for that in order to calculate the relative neutralizing value are going to be the fineness factor and the calcium carbonate equivalent. Now you'll have to calculate the fineness factor, and I will typically give you the calcium carbonate equivalent. So the way that we kind of describe this, we have these series of sieves, and we pass this material through these sieves, and that kind of gives us an indication of what the fineness is. And so the more fine a material, the more reactive it is. So for this particular material, we have a liming material where 3% did not pass through a 10-mesh sieve. This is worth nothing to us. This does not have any value or reactivity. Next, about 17% passed through a 10-mesh, but not a 60% mesh sieve. And this has a 50% effective, like it is 50% of that material is likely to react. So that would be 50% or 0.5 times 17 times 17 gives us 8.5%. That is the efficiency of that material. And then everything else that does pass through that 60 mesh sieve is 100% effective. We expect all of that material to react. So we get 100% of that, gives us 80. We add those values up and that gives us the fineness factor of 88.5. But remember, we need to, what we need is the fineness factor plus the calcium carbonate equivalent. So I have given you a table where X% did not pass through a 10 mesh sieve, Y% actually passed through the 10 mesh but not the 60 mesh. That's going to have a 50% effectiveness. And then also for a certain percentage passing through the 60 mesh sieve. So we do not get a value for 16. None of this is reactive. Half of 39 is 19.5. When we add 19.5 with the 100% effectiveness of the material that actually did pass through a 60 mesh sieve, we'll come up with 64.5. So this is the fineness factor for this material A. And then you would just continue to do that for each of those materials. All right, for the calcium carbonate equivalent, typically the co-op may know this. They should know this. There should be like a guaranteed analysis of this material. You can actually request to have a different type of material, a more faster reacting material, a more efficient or a potent liming material, such as something like calcium hydroxide. This is something that we typically use in labs because it has a very quick reactivity. And so the molecular weight, now I don't know if they just got lucky with this calcium carbonate being 100 grams per mole, but calcium carbonate 100 grams per mole. So the lower the molecular weight, the greater the reactivity of the material. And so the greater the reactivity of the material, the less of it you need. I will typically provide you with the calcium carbonate equivalent, such as in this example. So we're going to take that liming material from our example. We will calculate the R&V. We know that the fineness factor was 88.5%. That needs to be changed to a decimal. Our calcium carbonate equivalent is 80%. That needs to be changed to a decimal. Excuse me. We will multiply 0.885 times 0.80, which gives us 0.708. Multiply that times 100, which will give us the percentage as like a whole number of the relative neutralizing value. So you might be able to call the co-op and say, hey, do you have any information? What is the R&V of your material? And they'll tell you about 71%. It's possible that they know that information. They might not have the R&V calculated. You might need to calculate the R&V, and this is how you would do that. So this relative neutralizing value, if we think about our fertilizer calculations, becomes the new analysis of this liming material. So instead of it being 100% calcium carbonate and 100% reactive, it's only 71% 100% calcium carbonate material. So we're going to set this up just like we set up our fertilizer problems, rate over analysis. So the soil test recommended that we needed 1 ton of 100% pure calcium carbonate, 2,000 pounds. In 1 pound of example material, there are 0.708 pounds of calcium carbonate. When we do that calculation, we come out with about 2,825 pounds of this material. So the soil test recommended 1 ton, but because the co-op did not have a very pure material, we actually need almost 2.5 tons more. We need 2.5 tons of material almost in order to meet the lime recommendation. And I had plenty of practice for that on the calculation 2. All right. So next we would like to calculate how much fertilizer material this is going to cost us and how much that's going to cost us for an entire field. You may end up being a farm manager and you will be tasked with budgeting how much money it will cost you in order to operate your field. For this example, we just kept it real simple. We have a 100-acre cornfield. Our soil test recommends applying 200 pounds of nitrogen, 25 pounds of P2O5, and 170 pounds of K2O. I will give you the fertilizer material which you should use. I will ask you to calculate the amount of each fertilizer per acre, also the total weight of each fertilizer material for the entire field. Not difficult. This is simple rate over analysis. So our rate over analysis, we have 200 pounds of nitrogen divided by, and in 1 pound of 4600, there are 0.46 pounds of N. We need about 435 pounds of urea per acre. To make it simple, we just have a 100-acre field, so we need 43,478 pounds of urea. We would do the same thing for our P2O5, rate over analysis. That comes out to needing only 54.35 pounds of, this is actually superphosphate per acre, times how many of our acres we need. We know that we need 5,435 pounds of this material per acre. Next, we do the same thing for K2O. I've given you the recommendation of 175 pounds of K2O and 1 pound of muriate of potash. There are 0.6 pounds of K2O. We need about 292 pounds per acre times 100 acres gives us 29,167 pounds of muriate of potash per the whole field. That's pretty straightforward. I've been setting y'all up to be able to know how to do this rate over analysis. Next, we need to calculate how much this costs per ton. And what I like to tell students is like, you need to know how much things are actually costing you. So when I go to Walmart and I'm looking for some food that I'm buying, one instance that I like to use is mustard. I will try to buy mustard or things like that in bulk because I can get it for cheaper. Now the price coming out of pocket might not be cheaper than the 99 cents for the little small thing of mustard, but on a per ounce basis, it is cheaper. So I actually use this a lot in my life in the way that I actually shop for my food because I'm trying to get the most value for my money. So you were given a cost per ton. It costs about $394 per ton of urea. This is a fairly accurate price. So this is price over product. This is how we determine this. So price over product gives us how much it costs per 1 pound of fertilizer material. And if you know how much 1 pound costs and you know how many pounds you need per field, you can calculate how much you need or what the cost is going to be per that entire field. So when we do this math, 394 divided by 2,000, because there's 2,000 pounds in a ton, we find that our fertilizer material costs us about 19.7 cents or $0.0197. Next, we know from our previous equation, from our previous math, that we need about 435 pounds per acre times $0.197 per pound. That is about $85.65 per acre. Multiply that times 100, and we know that for the whole field, our urea cost is going to be $8,565. We do the same thing for our superphosphate. it costs $291. That comes out to be about 14.6 cents per pound. We do the same math. We come out to about $8 an acre for our phosphorus costs. Multiply times 100 acres, $794 for our phosphorus in that field. Do the same thing with the K2O. I see that I made that mistake. I'll fix that. This is actually there we go. Problem solved. We know that we need that we have $473 for this ton. That comes out to be about 23.7 cents per pound. From our previous calculation, we know that we need about 292 pounds of muriate of potash times 23.7 cents per pound gives us a cost of $70 per acre, or $69.13 times 100 acres. That's going to be about $6,913 in phosphorus in muriate of potash for our field. All right, that's pretty simple, straightforward math. I just don't know that maybe you have seen this price over product and then multiply times the number of pounds. So like in the problem, I have you specifically break it down to pounds per acre and cost per pound. So if you can break it down to what it costs you per pound and you know how many pounds of fertilizer you need, you can quickly calculate the cost of that fertilizer. All right, that's all I got for this video. I will see y'all on Friday, October 8th. All right, have a good weekend, or a good week ahead, I'm sorry, since this is Sunday.